So I can look at this and tell that this is a lithium atom, but you need to ask yourself, how can you do that? Because you might get one on the test that looks like that, but not as pretty. That one's actually pretty uniform. But how can you look at that and tell that it is lithium? First off, count how many protons are there. And be sure you got your periodic table out, because this is going to be something very essential to help you with. But anyway, how do I can tell that this is a lithium atom? Count how many protons there are. And protons are the positive ones. How many do you see? 3. 1, 2, 3. How many neutrons? 4. And how many electrons? 3. So what do you notice about the protons and electrons? They are the same. Y'all see that? 1, 2, 3, 1, 2, 3. That in a normal neutral atom, that's what it's going to be. Now, the neutrons, I'll go ahead and tell you, they're like fat of the atom. They're just there. They're the extra weight. They would give it the mass. Protons contribute too, but you can't change the number of protons without changing the identity of the element. So in other words, what I'm trying to say, I know this is lithium because there are 3 protons. What is the atomic number for lithium?
3.
How many protons does lithium have?
3.
Guess how you can figure out how many protons it has just by looking at this? The atomic number. So that is actually the most important thing on the periodic table, in my opinion, is the atomic number. That tells you the identity. That right there is basically the driver's license for the element. In other words, that's their identification. In other words, if you change the number of protons, you change the element. And that's not very easy to do. You can't really do that. How we form some of these other elements, and we will talk about it a little bit later, we clashed them together. We stripped the electrons and made them run into each other at the nucleuses, and that's how we created some of these other ones. I don't want to say create because that does go against the technical definition, but we kind of just smushed them together. But anyway, if I were to add a proton in here, this is no longer lithium. It then becomes the next element down the line, beryllium. You see, and if I add another proton to that, it's going to become boron. However, you just can't throw protons in. You got to throw in other things such as neutrons to balance things out. Basically, if you see a picture of an atom, count all these things. I would say you can go by the electrons on identification, but don't. We can easily, and in fact, later this week when you go in the lab, we can easily add and remove electrons like that. Yeah, that's not hard. They're on the outside. The guys in the middle are a little bit more difficult. So that's why actually we count how many each of these guys are. And you can actually look on your periodic table and count how many they have. We only talked about the protons right now. But guess what? The atomic number just doesn't tell you one thing. It tells you 2 things. It tells you the number of protons and the number of electrons. The only problem is it does not tell you the number of neutrons. You're going to need another number for that. But let's look at a periodic table first before we do all that. So this is another colored looking periodic table. I like this one. It's kind of traditional to the one that you see up on my wall. Pretty much other countries do use it too. So let's zoom in. Whee! Let's take a look at the lithium again. So in case you're not looking at yours, you can look at this one too. So we look at the atomic number. It's like, how does the number of protons and neutrons and electrons compare to these numbers? Well, the number 3 that you get up there, we already said, was the number of electrons and number of protons. But where do we get that number 4 that we had earlier? The 4 neutrons. I'll give you a hint. You have to do something with the numbers up there. Okay, so subtract the mass number and the atomic number. Now, hold on. Let's take a look. This is a decimal, okay? One reason why this is a decimal is because of the isotopes, and that's what we're going to talk about today a little bit, is isotopes, and we're going to do something with M&Ms tomorrow. So you'll notice this is 6.9. We can't really have half a neutron or a point of a neutron, so what do you think we should do here? Round. So that would be the number 7, okay? This is an atomic number. That's where we get our number from. 7 minus 3 will give us 4. In other words, if you have 3 protons, whenever you subtract it from the other weight, you get the missing variable, which is the number of the neutrons. So, in other words, the protons and the neutrons give the mass of the atom, right? We said that a second ago on that chart. Well, when you add these 2 together, you get the mass number. All the mass, again, comes from just the protons and neutrons. Remember, the electrons hardly weigh anything. They don't barely even affect the the whole mass. They do have mass, but they're so tiny, it really doesn't contribute to anything. So let's zoom in just a little bit more. Talk about the atomic number a little bit. So this is more of some of the nukes you need to know. Atomic number tells us, now we're getting to the note part. I was doing samples first. Got to mix it up a bit. Atomic number tells us the number of protons in an atom. It is found on the periodic table. For example, there are 7 protons in an atom of nitrogen. What's the atomic number to nitrogen? 7. Good job. Also, uranium has 92 protons. Its atomic number is 92. Everybody gets that. Yeah. Like, okay, I get it. Atomic number, protons, yay. It's when we start talking about the mass starts giving some people problems, but we've tweaked it in the past. The number of protons in an atom makes the atom what it is. For example, we already said this, potassium has 19 protons. It can never have any more or less than that and still be potassium. If it had 20 protons, it would be calcium. If it had 18, it would be argon. All right, individual atoms are electrically neutral, which means they have the same number of electrons as protons. So not just does that number tell you one thing, it tells you 2 things. If it is neutral, it also tells you the number of electrons. However, we'll start getting the charges a little bit later in the week. We're not going to start on that now, but the number of electrons can change. In fact, that's actually how it really happens. It really never stays neutral unless it's a noble gas. Anyway, those are some good ACT questions, actually, they bring up. Okay, so let's talk about the mass number. This is where it gets interesting. The mass number, which is usually on a periodic table located at the bottom of every box, tells you the sum of the protons and the neutrons. So just like we talked about earlier, if I said I have 3 protons and 4 neutrons, my total mass is going to be 7. That would be the mass number. So in other words, the formula basically to figuring out the neutrons is the proton or the atomic number minus the mass number. You subtract those 2 numbers, and that's actually how it'll always work out. But there are a few rules to that. When do you round? When do you look at this? Okay. So sometimes we talk about specific isotopes. For example, in this example right here, chlorine-37. They're talking about a specific type of chlorine. There are other types. There's chlorine-35. There's chlorine-36. This is chlorine-37. All that number tells you is the mass number. All that number tells you is the mass number. All that number tells you is mass number. Okay. So, but wait, on your periodic table, they say that number is the average mass number. Notice the difference between the two. Average mass numbers, they take in consideration all the different types of chlorines, and they average them together, giving us an average mass number. So that's one reason why sometimes you might want to round on the periodic table, but you need to know when you're going to do that. If they give you chlorine-37, you use this as your mass number. If they did not give you a number, you then use the one off the periodic table. And I am going to go over that a little bit more later. But anyway, you can look at your periodic table, find chlorine. It is atomic number 17, 37. 37 minus 17, you can do that in your head. Gives you 20. So it would have 20 neutrons. Do you realize that the mass number is not the number of neutrons? Many people write that down on the test. Oh, that's the mass number. Or that's the number of neutrons. Nope. It is the total mass of the whole thing. Also, aluminum-27. Its atomic number is 13. The mass number is 27. You subtract the 2, and you get 14.
So those are isotopes of chlorine-37?
Yes. Every element has a certain kind of isotope, except for the newer ones that we have, because honestly, they haven't been in existence for over pretty much a certain amount of time. They dissipate as soon as they are made because they're just so unstable. That's one reason why I say we're never going to get to the 8th energy level because everything now is just so unstable. You're already trying to build something on sand. That was a good metaphor. All right, so anyway, do know the difference between these two guys. They will help you out. What is the difference between the mass number and average mass number? I put it in a certain section here because people kept getting them mixed up. And so I'm going to give you basically the rules here of how to know the difference. So let's go back to our lithium that we were talking about. All right. The mass number is just the sum of the protons and neutrons of a specific atom. For example, if we have 2 different elements, oh, actually, they're both the same element, but they have 2 different masses. They're the same guy, but with 2 different two different sizes, okay? One's just a little bit bigger than the other. So if you have lithium-6 and lithium-7 is going to be one mass number a little bit heavier than the other, okay? So when we're looking at this, we also take consideration the population of how many lithium-6 are that size and how many versus the lithium-7. So for example, this has already been predetermined. You don't have to figure it out. But basically 92.5% on the planet, if you find a lithium atom, you have a 92.5% chance of finding one that is lithium-7. You have a 7.5% chance of finding one that is lithium-6. Does that make sense? They're the same thing, but they're just different sizes. That's it. That's the only difference. So you're more likely to get a heavier one than actually a lithium-6. Both are lithium, but one has 3 neutrons and the other has 4. That's the only difference between the two. One is more radioactive than the other. Okay. Okay. So think of isotopes like twins, but with different masses. No, not every twin weighs the same. That's just basically the big difference. Okay. So isotopes deal with neutrons. Okay, so average mass number includes both of these specific types. So how did we figure it out? So we took those percents earlier. We moved the decimal over twice, right, to put it in decimal form before you try to figure out how much of that is a percent. So for example, there was only 7.5% of the 6 lithium, or the lithium-6. So what we did was just multiply that and we get 0.45. Do the same thing to the 7. That one had the majority, which was 92.5%. We move the decimal over twice, multiply by it, and we get the 6.48. Add them together, you get a number that's very close to the number that's on your periodic table. Now, if you get a different periodic table or you look on another one, you're going to see that they vary year to year because we figure out different abundances on the planet all the time. And so therefore, we got to adapt the periodic table to that standard. So if you do look at an older periodic table or a newer one, you're going to end up probably seeing something that's a little bit different. But on average, they tend to kind of be the same. So for example, if you still rounded that average mass number to a whole, you would get 7 like we did earlier. Okay, so that's how we get the average mass number versus a normal mass number. Mass number is talking about one specific type of atom or one specific isotope of it. The average mass number is considering all those isotopes together. So let me get more specific. So how many neutrons does a lithium atom have? So if I did ask you that. We go with the mass majority. Since the majority of the lithium has a mass of 7, we go with that number. In other words, that's why you would round that number to a whole. Majority is already close to that, so we just kind of go with that. We kind of assume whenever you go out there and you get a lithium atom, if you were able to go out there and do that, you got about a 92% chance of getting one that is, your odds are going to more lean to the 7 than the other guy. It's not that big of a deal. To do so, we just round the average mass number to a whole number to make it the mass number. That's only if, though, they don't give you a specific mass number. So now I'll get to my more specific example. When to do what? Okay. So this only applies if the mass number is not given with the name. Is not given with the name. So for example, if I say lithium, you look on your periodic table, you find its mass number, and you round it to a whole, which would be 7. If I said lithium-6, though, the mass number is 6. If I said lithium-7, it's 7. You're going to get questions like this all the time. So you do need to know when to use what mass number for what. So if there is not one there, you look on your periodic table. The atomic number tells you the number of blank in a neutral atom.
Proton.
It does tell you protons,
And electron.
but it did say neutral, so therefore it's protons and neutrons. Some of y'all jumped ahead there. Do you realize it does say neutral? Remember the lithium atom we talked about earlier? They had the same number of protons and electrons. Number 2, the number of neutrons is, the number of neutrons in an element is equal to, is it the mass number? See, that's another good one, yes. So it is the mass number minus the atomic number. That's the only way you can get the neutrons. I like putting that one in. Y'all were paying attention earlier. So, number 3, the atom is mostly composed of. Oh, good, you got me there. I thought I put that question somewhere. Number 4, the element carbon-14. The 14 represents the number of neutrons? Protons and the neutrons, because this is the mass number. I'm going to have to learn how to write the letter N. And remember, the mass number is equal to the protons plus the neutrons. Forwards and backwards. Seems like that's going to be a trend in here. All right, number 5. Which of the following subatomic particles has the least mass? Hopefully you said the electrons, because they are also moving at very high speed, and if you look back at that chart, they have approximately 0 AMU. You realize the neutrons have 1 AMU, and the protons have 1 AMU. So the one that has the least is the electrons. Remember, they're also moving very, very fast. They're like kindergartners jacked up on Mountain Dew. All right, so you've heard about carbon dating, right? Okay. Well, there were some misconceptions in the 90s, and we got that. And my teacher said it was how we date things, and it was a foolproof dating system. It turns out that it isn't, because they started getting weird numbers, and it was actually a political stunt kind of thing to start funding for other projects and stuff like that. But I'm not going to go too much into the paranoia. But anyway. So if we take a look at carbon dating, everything has carbon in it. All living things do. That's why you're called organic life forms, or organic, which means has carbon. You would not be together, or your body would not be put together right now without that carbon. So pretty much every living thing has this element. It's very essential. It basically bonds everything together. Polymers have a big deal with carbon. But there's normal carbon, which is carbon-12. Then as we get going down, we get to carbon-14. You'll notice, though, the world's population of carbon-14 is less than not even a percent, but even 1/100%. It's actually pretty low. Percent abundance, if you look at the number, you'll notice it's like 12.01 on your periodic table. That's because almost 99% of it is carbon-12. The rest percents are actually very, very low, which is kind of crazy when you think about it. But anyway, again, FYI, radiocarbon dating and all this kind of stuff. You do not have to write this down, but this basically kind of talks about how it actually is used. Because of its decay, it actually and it does it at a certain rate. And because of that certain rate, we're able to actually date certain things. However, it is kind of tough because there's a range, and it only works at a certain range. Some people try to date dinosaur bones with radiocarbon dating, and that's what they tried doing, and it turns out that that was actually false. They can do it up to 6,000 years old, but pretty much after the 4,000, 6,000-year-old time, it gets unprecise. So it's like, how do we date other things? Well, there's other types of dating besides just carbon dating. There's argon dating, for example. There's many other things that we could use that has to deal with these isotopes. So from that, we get kind of a range. But that was one of the big myths, that carbon dating was like the most precise thing. It gets everything right. And then that was actually, that was false. It's good for dating a mummy, but for dating something that just killed over last year, it's probably not going to give you a very good accuracy. Again, it has to be like 100, 200 years old. So sad. But that does get us into other things. So everybody knows what this is: mushroom cloud, nuclear explosions, fallout, Holocaust, things like that. So let's ask you a history question real quick. What two main nations were involved in the Cold War conflict? Soviet Union, which is, now has turned into Russia. But the Soviet Union and, y'all just said the other one, America. So there's also Cuba that was involved in this, but y'all remember the Cuban Missile Crisis and things like that they talked about in history class. A lot of people at that time built shelters. But anyway, yes. So these two guys were involved in this conflict. So anyway, believe it or not, Mississippi, in fact, Lamar County was actually involved into this whole Cold War conflict. It's not that we sent soldiers or anything, but it mainly had to deal with the testing of the salt dome. So we're going to talk a little bit about Backfill, and you know where Russia is located, and you know where U.S. is located. But let's talk about Backfill. It is a very small town. No, I'm not from there. But it is in our county, and it's a K-8 school and all this kind of stuff. And honestly, there's not much there. The population's very, very low, which makes me think another reason why they wanted to test this place out. So anyway, if we keep zooming in, you actually see where Lamar County is of that. Backfill's off to the side, a little bit more closer to Marion. But there's something called the Tatum Salt Dome. It also was called Project Salmon. But basically there is something called the salt dome, and no, it is not above ground, it's below ground. I used to think it was like, for example, like an igloo. It was a big thing of salt. But no, it's actually below ground. And they always come back, Hattiesburg American always comes back and actually does stories about it. It's always kind of interesting because it's something that actually happened. The article all talks about how some people now, they actually still remember it, and in fact, it actually shook their house. They went and paid the people $5 to $10, depending on how many people they had in their house within the certain area, for any damages that's about to be done. Good. I think it was 62 and 63 that they set it off. One reason why they were doing a nuclear bomb underground was because of testing for shockwaves. Here's the thing. We were worried about nuclear war from Russia, or sorry, the USSR. So basically, if they were saying that they were not testing nukes and all that, but we want to be sure. Here's the thing. If they're testing them above ground, a lot of people are going to see it. It's kind of hard to hide that, right? So we were worried that they were testing them underground, which is a little bit safer because you don't have nuclear fallout and things like that. So to be sure, basically, we used the salt dome in Mississippi for this purpose, because we knew that the shockwave would basically see if they were actually testing them over there. Because obviously if you send out a shockwave, we're going to have the Richter scale, and it's going to send out a certain vibration. However, we needed to calibrate our instruments. We can't just detect, oh, there it is. We had to actually test it ourselves. So what we did was that in Baxterville, there is this place called the Salt Dome. It's underground, and it's basically like you think, a gigantic dome of salt. And you're like, salt? Yes, the salt that you put on your food, like salt, okay, that kind of salt. It's NaCl. But it is so thick, and I'm going to give you a sample here, and this isn't really part of the salt dome, this is just a quartz, but it gives you a good visual idea of what's going on. When, like, molten rock and all that kind of stuff is forming underground, some of it gets trapped, and it makes kind of like a bubble. It's probably not that perfect. But what happens is water gets trapped, and it moves towards the center because of its polarity. Eventually, that water dries out or evaporates, and you're left with a hollow center. So the dome itself is not just one big chunk of salt, but it is salt through here, but it has a hollow middle. This is a quartz that you see right here. And basically imagine the whole circle or a whole dome of it or a big gigantic rock of it. But if you crack it open, these are very cheap, by the way. This is like $7. So don't think that this is very expensive. It's so pretty. But basically on the inside, the salt forms just like this. Just probably not with the nice little colors that you see here. And no, I'm not going to lick it to see if it's salt. But that's actually what's going on the inside, is that little hollow crystal little structure that you see. So what they did, because this thing is very thick, they basically drilled a hole down into the middle, dropped off a nuke inside, and set it off, okay? They told people over at Berkeley, California to start calibrating their instruments, like, hey, we're about to set off, see how long it takes for it to get there. So they set one off, waited another year, came back and set off another. And basically they were able to calibrate their instruments to see if the USSR was actually testing nukes underground. Allow me to show you the next picture here. But that gives you an idea. Y'all seen these before. Okay, about radiation. So if you do it underground, the radiation can't escape because, honestly, radiation cannot go through thick objects. That's one reason why they say use lead. But obviously, earthquakes did happen around there. You see the old-timey pictures of all the chaos and everything. But basically what happens, it would send off a shockwave. People over there in California had their instruments calibrated, so they were actually able to pick up the signs. And so if Russia was testing nukes, we would know about it, and we'd be able to actually launch a preemptive attack and things like that. But turns out that they weren't testing it, sadly. I know, it would have been more exciting if they were. But hey, we had something to do. We set off a bunch of nukes underground. So that gets us back to the isotope thing. I told you that story to tell you this story. But believe it or not, how does this affect you? Well, this is salt. What else is underground?
Oil.
Oil, yes, oil is underground. You're not wrong there, but the oil's a little bit more down there. What's?
Molten lava.
Well, that's even further down. What's the other one?
Water.
Water. So when it rains, you get groundwater and all this stuff. And does salt dissolve in water? Yep. So what's going to happen is eventually over years, it's going to start dissolving that dome. And so eventually this is going to get out, or whatever is in there, radiation can get out into the water supplies. The pictures that you see up there are the 3 isotopes of hydrogen, and it's pretty much the only ones that are have a specific name. So if you're wondering why it says protium, deuterium, and tritium, those are not elements. They're all hydrogen, but they're different isotopes. We use that because hydrogen is the most simplest element on the periodic table. It consists of 1 proton, normally, and 1 electron. It doesn't have any neutrons. But when we start throwing in the neutrons, this is where stuff starts happening. It becomes unstable. However, if you do ever find tritium, it is worth, let's see, what is it? I think they said $60,000 per gram, if you do find tritium.
How do you find it?
Well, there's one place to go look. Tritium is very, very radioactive. Deuterium is not so much. It's not too bad. It is a little bit bad. But most of hydrogen is going to be the protium that you see here. One reason why it's called protium is because, well, it's just a proton. I mean, we can remove that electron if we want, then it's just a proton. And we do it all the time. If we add in a neutron, the mass number is 2. One reason why it's called deuterium, aka deuce, deuterium, that means 2. And tritium, obviously, because its mass number is then 3. But basically, tritium is the one that is the H-bomb they talk about. It's so unstable, all you got to do is ignite it, and what happens is those neutrons go flying off and hit other atoms. This is how we get something called a nuclear reaction. It's one reason why the nuclear bomb is so deadly, is because depending on how much is actually ignited, it depends on how much of the radius it's going to cover, because it's a chain reaction. And again, I have the little pictures that are located up here. For example, when uranium breaks down, these atoms or these neutrons are very heavy. They're going to get through the electron cloud and hit another atom. And when they hit another atom, it's just like playing billiard balls or pool. It's just like when you hit that pool ball, it's going to knock all the others out. So if you knock out all the other nucleuses, they're going to go flying. They're going to hit other nucleuses and so on and so on. And then you get the idea of the mass mushroom cloud that happens after that. That's actually how a nuclear bomb works. All right, so isotopes. So Dalton was wrong about all atoms having of the same element being identical. That was the other one. So that was, I believe, his second one. So he was kind of off a little bit by that. So that's when we did talk about the isotopes. Atoms of the same element have different numbers of neutrons, thus different mass numbers. And this is what screwed up Mendeleev when he was trying to organize the periodic table. So when he was getting certain mass, he may have got some that were a little bit different, and it kind of messed up like who should go first. So this is one reason why we do it by atomic number instead of mass number now. These are called isotopes. You need to know the word isotopes means they change with neutrons. They vary in neutrons. Because there's going to be another guy called ions, and they vary in electrons. But we'll talk about them a little bit later. These vary in neutrons. So when I say like chlorine 37, chlorine 36, chlorine 35, they're all chlorine, but their isotopes are the 37, 35, 36, that kind of thing. All right. And this is next for the last thing here. Elements occur in nature as a mixture of these isotopes. So we've already figured out all these guys. For example, we just talked about the chlorine. 35 and 37 both have 17 protons, but one has 18 neutrons and the other has 20. One's just a little bit bigger than the other. There's no way of predicting the isotopes exist for each element. These have been done already for you. Anyway, so naming isotopes. We did talk about how to kind of name them when you see these little numbers pop up on the sides. So the number written after the element is always the mass number of a particular isotope of that atom. So carbon 12, the mass number is 12. Carbon 14, the mass number is 14. But uranium 235 is a certain type of isotope also. The mass number is the number of protons and neutrons in the nucleus. So I gave you all this formula the other day, but again, it's up there now. God, it's so hard to do. So basically, you try to fill in the chart. And I'll go ahead and give you a quick sample of what they're expecting you to do here. So you'll see little questions like this. Okay? So for example, you got oxygen, and you'll need your periodic table, otherwise you're probably not going to figure out some of this stuff. Okay, so if you don't have it out, that will help out, because that does tell you the atomic number, which is essential here. So oxygen, okay? They have a blank right here, which is your mass number. So whatever you get here is going to be the number that goes in front right here. Okay, y'all with me so far? But the mass number, to find it, you need the number of protons and the number of neutrons. Well, you'll notice right here, they only give you the number of neutrons. You're missing the number of protons. But they did tell you the element is oxygen. So how can you figure out the number of protons by knowing if it's oxygen? Periodic table. So, and what is the atomic number of oxygen? 8. It is 8. So if it has the atomic number of 8, then 8 goes here. But that also tells you something else. Also the number of electrons. So basically these two columns are going to be, whatever you have here is going to be the same thing here. And then you can figure out the mass number. So it's a lot of, you got to fill in this, to fill in this, to fill in that. It's a puzzle. And that's actually what the homework is tonight. So we already talked about oxygen. We said the protons was atomic number 8. Therefore the electrons are going to be 8 also. But however, if you add the two protons and the neutrons together, you get the mass number, giving us 8 plus 10, which is going to give us 18. All right, so we did that as a sample. This one, they did not give you the element. They did not give you the mass number, but they did give you two things you can use. They gave you the number of protons, which also gave you the number of electrons, which we already said. And if you know the number of protons, and remember, that's the ID. What atomic number is 33? Arsenic, which you do not want to eat because it'll kill you. So you add these two together to get the mass number, and so we get arsenic 75. I can't ever tell you exactly where to start because you kind of got to look until you get it. My thing is this: if you get the number of protons, you solve majority of the puzzle. So always try to get that. Remember, because I always said like that's the important thing, because once you get the ID, you're good. They already said number 15, which is phosphorus. They already gave you the mass number, but they didn't give you these other guys, but they gave you this. So what you had to do was actually subtract. Oh, but they also gave you this right here, which filled in that gap over there. So 15 minus 31 gave you 16. All right, so the symbol notation, which is one of the things we're going to talk about. And don't worry, we're almost done. Contains the symbol of elements and the mass number and the atomic number. So you know how on the periodic table you have the atomic number on top usually and the mass or the average mass number on bottom? Well, in symbol notation, it's backwards. You basically take the symbol and you put it where this X is. That's what that really means, is the X. Let's try it on the 3 we just did. Oxygen 18. How would we write that? And yes, all the numbers are on that chart that you use. So 18 over 8. And this is what it would look like. O G. Mass numbers on top, others on bottom, and you can easily look at that and tell that's going to be 10 neutrons. 18 from 8. Let's do the next guy. Arsenic 75. What goes on top? What goes on bottom? 75, 33. That's some weird measurements, but all right. And phosphorus 31. What goes on top? What goes on bottom? And that's all it is to it. A lot of people go right to, and that's one reason why I do this question. Blank is an isotope of hydrogen that has 2 neutrons and 1 proton. Okay? So if you have 2 neutrons, and how much do neutrons weigh? They have each weigh 1 AMU. So you have 2 of them, therefore you have 2 AMU. If you have 1 proton, they also weigh 1 AMU. So 2 plus 1, that gives you your mass number. Do you realize the reason why it's called protium, deuterium, and tritium is because of the mass number. So this one is, if we wrote it out, was 3/1. This is radioactive. It's called tritium because of the mass number. One reason why I brought this up is because, again, that is what a lot of people go right to. It's like, oh, 2 neutrons. That's the mass number's 2. Yes, it is, but it's also, don't forget to add in your protons. And that's what it goes by. Okay? By the way, that's also the pictures that are in your notes. All right, number 2. You should be able to get this one. Isotopes are atoms that vary in... Neutrons. It is neutrons. That's what we've been talking about the past couple days. They never vary in protons, and we haven't talked about this, but if they do vary in electrons, which is tomorrow, they're called ions. If they vary in neutrons, they're isotopes. I'm getting ahead of myself with the ions, but it's good to go ahead and know. All right, number 3 and number 4. All right, this does bear talking about. Number 3, 3 isotopes of carbon are indicated in the picture. They're talking about right here. How are these isotopes alike? Okay, what do they have in common?
The same atomic number.
They do have the same atomic number. So this also tells you, the atomic number tells you protons and electrons. Well, they don't give you electrons here. So they give you the same number of protons and also the same atomic number. The mass number and the neutrons are not going to be the same, as you can see up here. This one has 6 neutrons and a mass number 12, 7 and a mass number 13, and 8 with the mass number 14. I don't know why I went blank on that. So which one has the same?
C.
That would be, I think it is C. Yes, it is C. That is a good question.
It's a good question.
That is a good question. I like this one. They're all good, but this is a good one to study. So some people ask me, like, what is it going to be like on the test? Well, I have to put them in a certain form. They're not going to be just fill out the chart. It's going to be this. I have to put it in some kind of words because this shows kind of scientific reasoning. This one can be a booger if you don't know. Deuterium, okay, which actually is like that, but that didn't fill in for some reason. But deuterium, like tritium, so this was deuterium up here. What am I doing? Not a fraction. Like that, and, oh, sorry. Protium was this, and tritium was this. Okay, that's all in your notes. All right, and I probably shouldn't put them on top of each other. Anyway, so deuterium is an isotope of hydrogen. Scientists find that both of these reactions occur. Okay, so right off the bat, don't even look at this. Analyze. What do you notice is different between each thing? Right here and right here. Other than that, they're identical, right? They have similarities. So right off the bat, now look over here. They are not different. Now you got a 50-50 shot. Now you got another thing. They say that it's either going to be similar chemical properties or similar physical properties. Well, first off, let's go back here. There's 2 ways. This is, before you jump ahead, a chemical reaction. How do I know? 2 reasons. 1, I don't have the same stuff I started with. They're rearranged. They're in different compounds. That's a chemical reaction. Second off, it says the word reaction. And all reactions are chemical. So that one then negates out the physical. There's only one that is correct then. B.